Okay, this will be an introduction to torque and angular momentum. Keep in mind that these chapter titles don't apply to your book. This is a PowerPoint I found from a different book. So first we're going to talk about torque. Imagine you're trying to loosen a bolt here and you got your wrench hooked up to your bolt and you put your hand way down here at the inside of the wrench close to the bolt and you try to open it. Well, it's probably not going to loosen the bolt. So what do? You put your hand way down here at the end of the wrench because you'll create more torque that way. Because torque is the force you're applying times the distance in the simplest case when everything's perpendicular. Okay, so some definitions here. We call the vector along which you're applying your force. So we get this string here attached to this, it looks like a paint palette. This line here is called the line of action. Then we have the lever arm. That's a vector that's perpendicular to your force through the axis of rotation. This vector here would be called the lever arm. And we'll see in a little bit that the torque you apply is the cross product of those two vectors. So by convention, the whole scientific community agrees on this. We're going to call counterclockwise torques. If you're making something rotate counterclockwise, we call that a positive torque. And if you make it rotate clockwise, we call that a negative torque. So F1 here, imagine this thing is fixed here at this point O. F1 would make the paint palette rotate counterclockwise. F1 would cause a positive torque, but F2 here would make us rotate clockwise. That would be a negative torque. F3 wouldn't make us rotate at all because our lever arm and our line of action are parallel to each other, and the cross product of parallel vectors is 0. F3 would cause 0 torque. Okay, so we'll see here, this is the real definition of torque. Torque is the cross product of the lever arm with a line of action. But in the simpler case, remember the magnitude of a cross product is magnitude of the first, magnitude of the second, sine of the angle between them. So this is the magnitude of our torque. It'll be the distance you are away from your axis times the force you're applying times the sine of the angle between those two. Okay, remember torque is a vector and it follows the right-hand rule. The right-hand rule says you stick your fingers in the direction of R here, your lever arm, then curl your fingers in the direction of the force. In this case, the force points directly out of the page. It's pointing right here towards your eyeball. So R cross F. Then your thumb points in the direction of the torque. So in this case, the torque would be up. I think the best explanation here is imagine you're screwing or unscrewing a bolt. So if you were to turn this bolt like this, so the force is coming out of the page, we're going to rotate. If you were looking at it from above, it would rotate counterclockwise. Remember lefty-loosey, righty-tighty? That would loosen up this bolt. The bolt would rise. So the direction the bolt would go is the direction of the torque vector. Or if we were to turn this the other way, so if the force were going into the page, so from above, if you were looking at this from above, from the top of this bolt here, the wrench would be going around clockwise, lefty-loosey, righty-tighty. That would, you're turning it to the right, that would make the bolt screw in, so the torque would be down. Okay, some more information, or another way to think of the right-hand rule. The right-hand rule is you point your pointer finger in the direction of the first one. So point your pointer finger along R here. Rotate your hand so that your middle finger will point along F if you hold your pointer and middle finger at right angles. So your middle finger is pointing at your face right now. Your pointer finger is pointing this way. Your middle finger is pointing at your face. Your thumb tells you the direction of the torque. And that would point up. We'll practice some of those in a live session. Okay, torque is the angular equivalent of force. Anytime we're doing angular stuff, when we have alphas and omegas and whatnot, and thetas, then the angular equivalent of a force is a torque. So the rotational version of Newton's second law is the sum of the forces is mass times acceleration. That's just F equals ma, but with rotational stuff. Sum of all our torques is our moment of inertia times our angular acceleration. Okay, you can read that one on your own. We'll do some problems like this. Read all that on your own. So when an object is moving, we've already done a problem like this. If an object is moving and rotating, it will have regular old translational kinetic energy and it will have rotational kinetic energy. This comes from the center of mass moving around. This comes just from the rotation, and that will be our total kinetic energy. So there are two components to it. Okay, we talked about this before in the live lecture. Let's say you got to wheel your tire on your car. You're driving down the road. What does each part look like? So you're moving down the road, so forget about the rotation for a minute. Your entire car is moving to the right with speed v. Now, forget about the motion for a minute. Just imagine your tire sitting there spinning because it's also rotating. Your tire is spinning around with speed v. So notice this point at the top. It's moving with speed v and it's also spinning with speed v. So combined, the top of the tire is moving at twice your speed. But the bottom, you're moving to the right with speed v, but you're rotating to the left with speed v. So instantaneously, at all points, at all times, the bottom of your tire has speed 0. Okay, you can look through these examples on your own. This shows the relationship. So an object that's moving through space will follow Newton's second law. The sum of all the external forces on it will be the mass times the acceleration of its center of mass. And if there are any unbalanced forces on it that don't go through the center of mass, they'll cause a rotation. And the sum of all the torques, mass or force times distance from axis, times the sine of the angle, will be the moment of inertia times the angular acceleration. When we do static equilibrium problems, we're going to have to use both of these. Those problems are fun. This is just a diagram or a picture that shows you what causes something to roll down a hill. If you roll a marble down the hill, if our surfaces were perfectly smooth, it wouldn't roll. It would just slide down the hill. What's actually happening is some of the tabletop or whatever you're rolling down bunches up in front of it and causes a torque that causes it to rotate. That also causes a force which slows it down. That's why it won't slide down the hill as fast as it would if everything were smooth. Okay, you can look through those. Next we want to talk about angular momentum. Angular momentum is the rotational version of momentum, and it's just I, our version of mass, times angular velocity. This is exactly the same as P equals mv. P being linear momentum. In an isolated system, angular momentum is always conserved. Just like with regular momentum, remember the sum of the forces is the derivative of momentum with respect to time, while the sum of the torques is the derivative of angular momentum with respect to time. Angular momentum is a vector. just like omega was a vector. I don't know who typed this up. Somebody goofed there. That vector sign should be on omega. I is a scalar. I is not a vector. See here, omega is the vector. So if you're rotating around, looking at it from above, counterclockwise, imagine holding your hand in such a way so that when you curl your fingers curl around in the direction of rotation. Then your thumb points in the direction of the angular momentum vector, and that's the same as the direction of the angular velocity vector. If this sprocket were rotating around like this, then in order to curl your fingers around it, you would curl this way. Your fingers point in the direction of rotation. To do that, your thumb has to point down. So the angular momentum vector is down, and so is the angular velocity vector. Angular momentum is always conserved when the net torque acting on a system is 0. So imagine Einstein here is rotating around. We actually do this in the lab when we could meet face to face, but we won't be able to do this time. So we're rotating around, and he's holding the dumbbells way out here. If he pulls those dumbbells in closer, well, he's changed his moment of inertia. He's made his moment of inertia smaller, which then must make his angular speed bigger to conserve angular momentum. It's the same thing that happens with ice skaters. When they are doing one of their spins and they pull their arms and legs in closer, they'll spin faster. Okay, that's also what cats use so that they always land on their feet. They have to, angular momentum must be conserved, so they have to twist different parts of their bodies at different times in order to preserve angular momentum and rotate around.